All right, laissez-les bon temps rouler. We're going to talk about sigma notation, and actually there's, a bazillion resources for this already on the internet, so I don't know if mine's going to be particularly better than anybody else's. But, here we go. So that is a capital Greek letter, sigma, and it's used to notate a sum. And it's sort of a convenience notation. It looks complicated, which is actually really cool once you know how to use them, because if you want to look fancy, you can write a sigma. But the reason that we use them is it's really awkward to be writing these series all the time where you're saying like 1 plus 2 plus 3 plus ... up to 99. It would be nice if there was a more compact way of writing your series, and that's what sigmas let you do. So this capital sigma means that you're going to take the sum of a whole bunch of things. And so here's the way that you write them. You have a variable that's called the index, and the index tells you what number you're going to start at and what number you're going to end at. So I'm going to go from 1 to 99. So you say k equals 1, that's the starting value. What you write on top is the ending value. And then you write an expression using k on the inside here. So for us, we just want to add up each of these numbers one at a time. So that's just the k value. So the way you think about this is k starts at 1, and then, so you plug in 1, then you move k to be 2, and you plug in 2, and then you add those together. Let's do another example that I think is maybe going to make this a little clearer. So let's say k starts at 3 and goes up to 7, except this time let's do k minus 1 times k plus 1. So what's this equal to? When k equals 3, let's plug it in. So that'll be 3 minus 1 is 2, times 3 plus 1 is 4, so that's 2 times 4, and that's my first term. And then I'm going to add it to what I get when k is one value up, when k is 4. Hold on. Here we go. This is a better way of thinking about it. So k starts at 3 and goes one at a time up to 7. So here I'm going to have a term where k is 3, and a term where k is 4, and a term where k is 5, and so on. Each of these terms fits this pattern for that particular value of k. Yeah, this is how I should have explained it to begin with. All right, so when k is 4, that's going to be 3 times 5. When k is 5, that's going to be 4 times 6, and then 5 times 7, and then 6 times 8. And so that's my sum. So you can see that this is like a very flexible notation. You can write a lot of different sums down this way. Let's go the other way. Let's say I've got this sum. See how every single term has the same structure, the same pattern. I've got a number cubed minus something that's one larger than that number. So if I want to write this down using a sigma, I'll have to choose one of these numbers to be my index. So I kind of like using this as my index, going from 1 to 10. So this will be k equals 1, this will be k equals 10, and I'll have terms all in between. So I'll say, let's have k go from 1 to 10, and then the pattern for each term is going to be my value of k cubed minus 1 larger than k, so k plus 1. And that would be a shorthand expression for that entire sum. They're also convenient if you want to write out a general series without using all these variables. So here's a general arithmetic series where I have a starting value and I add d and another d and another d and so on. If I wanted to write that entire sum using sigma notation, I could start out. It doesn't always have to be k, by the way. You could make this variable down here be whatever you like, but k is conventional. So I'm going to start from 1 and then go up to, it looks like, what am I trying to get to here? Oh, what do I want to do here? I guess I want k to represent the term number. So this will be with k equals 1, this term will be with k equals 2, and it goes all the way up to the last term, which is k equals n. So 1 would be my starting value, n would be my ending value. And then every term has the same structure. It's a sub 1 plus some number of d's. How many d's? So in the first term, I've got 0, and then 1, and then 2. So that's always 1 less than my k number, because k equals 1 for the first term, and I've got 0 d's. Here k equals 2, because it's the second term, and I've got 1d. So it's always going to be k minus 1 d's. So this is a much more compact notation for this entire series. You don't have to, there are several equivalent ways of writing this. So let me write it again a slightly different way. Let's do sigma with k starting at 0 and going up to n minus 1. In that case, it's like my k number is describing how many d's should be in each term. Because k starts at 0, and here I have 0 d's. And then next k will be 1, and here I have 1d, and then 2 d's. And then at the end I have n minus 1 d's. So in this version, k is intended, I'm making the choices here, so I'm deciding that k is going to describe the term number, and then I'm writing down how many d's as a function of the term number. It's like related to the term number. Here, I'm choosing to have k have a different meaning. K is going to actually directly describe the number of d's, and so here I can say a1 plus kd. And that makes it turn out a little bit nicer looking. These are exactly the same. If you were going to actually write out the terms one at a time, in both cases you would end up getting this exact thing. So that's another reason this is convenient, is because by changing the index boundaries, like where you're starting and ending, you can sometimes make this expression simpler to think about. Let's do geometric. So, in a similar way, we've got all these terms. They've got the same structure, which is a1 times a power of r. So, if I wanted k to be the term number, going from the first term to the nth term, then the general pattern would be a1 times r to the k minus 1. If I wanted to have k describe how many r's are in each term, I'm starting with 0 r's and ending with n minus 1 r's, and in that case I'd have a1 times r to the k. Alright, we'll talk more about sigma notation later. Yeah, maybe this is enough for now. Okay, thank you.